My name is Shaquille Ankrum. This is a FIZ 2212, Lab 3, dealing with circuits. The purpose of this lab is to predict the behavior of circuits with different resistors, capacitors, and orientations. To do this, we use the principles of energy and current conservation, as well as Kirchhoff's circuit law and Ohm's law. And we'll compare this, we'll use these laws to form our expected values and then compare these values with modeled values using an online circuit simulator. Yeah. Fundamental physical principles in this lab includes Kirchhoff's circuit laws. Kirchhoff's circuit laws, I'm sorry about that. Including the node rule and loop rule, as well as Ohm's law, which has to do with the voltage, currents, and resistance. System surroundings and initial conditions. The system is the circuit. Surroundings is everything else. Initial conditions, we have two 1.5 volt batteries, 2 ammeters, and 2 resistors, 47 ohms and 100 ohms. Preview of the results. The current and voltage values found from the model pretty accurately match predicted values. This is likely, we'll get into it later, but most likely due to the fact that it's a model and not real life, so there's less room for error. And then also the magnitude and current is time dependent in an RC circuit. So in experiment part 1, predicted current was 0.2041, and the model current we got 0.02, not 0.02, that's a typo, 0.02. So like I said, pretty accurate to prediction. Reversing the connection of the ammeter, the reading became negative. And the reason why we had zero current is because the circuit was open, so there's no path for the current to flow. Here we see that Kirchhoff's law is followed as the total potential difference across the loop is 0. So we used using Ohm's law to calculate the resistance. We see that the resistance values are true to the resistor's true values. The calculated values are true to the resistor's true values. Here, and we connect the ammeter in parallel with the 100 ohm resistor, and we had the question of why doesn't the voltmeter change the reading, and that's because the voltmeter has a high resistance, so very little current flows through it. Here we see that parallel current splits into two paths, and that's what gives us the higher reading of 0.06. In part 2 of the experiment, we're examining RC circuits. We had a bulb connected to a 9 volt battery and capacitor in series. We went to measure the time for the bulb to charge and discharge with the capacitor on it. The 10 ohm bulb, you see, is 7.8 seconds to charge, 7 to discharge. 20 ohm bulb had 13.6 seconds to charge and 16.2 seconds to discharge. Putting this time into a graph, recorded the voltage and time across the capacitor discharging to get time dependent calculations, and it just tells us like how long it took for a line of best fit for the bulb to charge. And we see using the calculations, we can see that our experimental calculations was close to our expected calculations. Possible sources of error. The model's more than likely correct just because it's a model and not real life. But there is always, of course, the possibility of human error when recording time potential difference, and of course rounding errors. So what if you were doing this experiment in real life using an actual ammeter instead of an ideal simulator? What's different about a real ammeter and how would it have affected the circuit you hooked it up to? It would have a non-negligible resistance as opposed to the negligible resistance of an ideal ammeter, and this would lead to an increase in resistance and a decrease in current. And then if you were doing this experiment in real life, use a real battery to charge a capacitor with no resistor, how quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? No resistor means the circuit would, in theory, reach full charge immediately. However, this would not happen in real life because many components in circuits, wires for example, have some resistance, causing the capacitor to charge in a non-instant time.